2 or 3,000 years ago in ancient India, there was a man called Panini. For centuries before he was born, people in that part of the world had been chanting a Hindu religious text called the Vedas. Older generations who memorized this text would teach it to the younger generations, and through this they would pass on the knowledge and insights to the next generation, which they still do to this day. Over the centuries, scholars had devised many techniques to preserve the exact correct pronunciation and rhythm of the Vedas. However, some were concerned that this was not enough. While they could preserve the text of the Vedas, the language itself was changing. And if the language itself changed, the interpretation of the Vedas might change and the whole project would be compromised. Panini aimed to solve this problem. He studied with the elders of his time and devised a grammar for the language, a language which we now know as classical Sanskrit. He did this using a system of formal rules and transformations which could generate correct phrases. His work is called the Ashtadhyayi, and it's still read and studied to this day over 2,000 years later. His grammar would go on to influence Western linguists who were trying to come up with their own system of rules for their languages. And via this, a man called Noam Chomsky. Chomsky proposed that language in general is based on a system of rules, some of them innate and some of them learned. And of course the idea that language is based on a system of rules was very appealing to the early computer scientists trying to come up with the first programming languages, to the extent that Donald Knuth actually took Chomsky's book with him on his honeymoon. Knuth was struck that mathematics, linguistics and computing could all come together in this way, and that is about as little as I can bear to tell you about the history of parsing. It's not very fashionable these days to spend very much time on parsing, but I suspect this is not because it's unnecessary or uninteresting, but because it's so fascinating and intricate that you could easily lose weeks just digging into it. This is language, one of our most powerful and mysterious tools. By learning a little bit about parsing and how to create your own languages, you can steal just a little bit of the fire of the gods. I'm hyping this up just a little bit because the theory does just take a little bit of work to get through, but once you've got it, it's all fairly straightforward. Today we're going to talk entirely about parsing. First about generative grammars, then about recursive descent, and finally about pushdown automata. By the end of the video, we will have a regex parser to go with our regex engine to create a full regex machine. Let's get started. First, we're going to look at grammars. We'll use an example from last time, the grammar of a laugh. Here are some example laughs. They follow a few rules. They're made up of one or more ha's, and each ha must start with an H, then be followed by one or more A's. The rules for producing or recognizing a string are called a grammar. We could describe this grammar with a regex like this. This regex matches all valid laughs. It's also capable, if you wrote a program to do it, of producing strings that follow that grammar. The set of all strings that fit this grammar is called its language. Let's look at another way we can describe this grammar. This is a slightly modified version of something called Backus-Naur form, named after John Backus and Peter Naur, two members of the committee who developed ALGOL, one of the early programming languages. We'll talk more about John Backus in a future video, and you may remember Peter Naur from the Stacks video. Let me talk you through the syntax. We have here a list of rules, one on each line. They're sometimes called production rules, expansion rules, or rewriting rules. This operator, 2 colons and an equals sign, I'm going to call the rewriting operator. It means the thing on the left can be rewritten as the thing on the right. So let's talk about the things on the left and right. Start, laugh, head, tail, as well as those strings H and A are all called symbols. Those symbols come in two kinds, terminal and non-terminal. Our terminal symbols are the literal letters H and A. They are terminal because they don't expand into anything else. Notice that the strings in our language, in this case laughs, are made up entirely of the terminal symbols. Our non-terminal symbols are start, laugh, head, and tail. They get rewritten in the process of producing a string using the grammar. We can use this grammar, much like the regex, to recognize or produce strings in the grammar's language. I'll talk you through producing strings first. We begin with the start symbol. There's just one rule that tells us how to rewrite start, so we select that and replace the symbol on the left with the one on the right. Next, we look for rewriting rules with laugh on the left and find 2. Because we've got 2 matches, we can pick between them according to whatever criteria we like, or even at random. I'll pick the longer one in this case. We then rewrite laugh using the rule, getting head laugh. Next, we pick the first non-terminal symbol on the left, head. We find a suitable rewriting rule for that, and rewrite head with the right side of the rule, leaving laugh as it is to be handled later. We then keep rewriting until we have only terminal symbols. This is our produced string. By making different decisions at the points where we have multiple rules to choose from, we can use this grammar to produce any string in the language. Now, this theory is classically explained in this way because it comes from Chomsky and generative linguistics. And linguists, of course, were very concerned with how humans produce language. And while this might seem simple, this sort of thing formed the basis of their ideas. Now, for us as software engineers, or we may as well say computer scientists at this point, we're not so interested in producing computer programs based on random choices of what syntax to use. We want to go the other way, to take a sequence of symbols and determine its structure. That's what parsing is. I think the Dragon Book puts it quite nicely. Parsing is the process of determining how a string of terminals can be generated by a grammar. Take a look at this laugh on the left. It's a sequence of the terminals H and A in our grammar. Ask yourself, how would you, starting from the start symbol, pick the right rules to follow to produce this string? That task of figuring out how to produce a string given a grammar is exactly what a parser does. It's kind of a deep idea, and it absorbed a fair few great minds in the 60s and 70s. In our current era, the problem is largely solved for all practical purposes, but it does have a few rough edges. Today we're going to cover just enough to parse regular expressions. This will enable our regex engine from the last video to properly go from a regex string all the way through to a running matcher. But before we get into that, I'm just going to give you one or two more points about grammar. The first is that in computing, we typically represent a parsed sequence as a tree. So much so that a lot of people think about parsing as really the process of turning a string into a tree. If this was some sort of weird laugh-based programming language, we might call this an abstract syntax tree. But since this isn't a programming language, I guess it's just a syntax tree or just some sort of tree. You can see in this tree that all of the terminal symbols are in the leaves at the bottom, whereas the structure of the grammar is reflected in the non-terminals above. And you can sort of imagine parsing as the process of taking the nodes on the bottom and then constructing above them a tree that fits the rules of the grammar. Okay, and the second thing is perhaps not really necessary knowledge for where we're headed in this video, but it kind of blew my mind, so I'm going to share it with you. Plus, it's pretty useful for understanding the difference between a regular and a context-free grammar, so I'm going to share it with you anyway. We know from the last video that this must be a regular grammar because we made a finite state automaton that could recognize it. However, there is another way that Chomsky defines regular grammar, aside from just being interpretable by a finite state automata, and it is using these rewriting rules. For each category in the taxonomy, he has a sort of set of meta rules which define what the rules in the grammar must conform to. And these are the meta rules for regular grammars, that every rule in the grammar must be in one of these forms. Every rule must have a non-terminal symbol on the left and either one terminal or one terminal followed by a non-terminal on the right. There's also an optional special case rule for having start go to epsilon or an empty string, which you can only do as long as the start symbol is never on the right hand side. And I think you can broaden that rule out, but the more you do so, the more complicated it gets. So we'll just keep it like that. A few of the rules in our grammar on the right are not in this form. However, since we know it's regular already, we should be able to rewrite it so that it is. We'll need to rethink all of our rules, so let's start from the top. We'll begin with start, and of course it's going to be a non-terminal symbol. So we'll define it as H and then another non-terminal called tail. H because of course our laugh has to start with H, and then tail will have to somehow expand to the whole of the rest of the string. We know that the very least tail will have to be is A, so let's define a rule for that. But we also know that tail will sometimes want to expand to an A followed by another A. We can handily define this by saying that tail can be A followed by another tail. Tail can also be followed by an H to start another chuckle, and we can define a rule to handle this case too. Tail can be A followed by a symbol called head, which we can define identically to the start symbol. H followed by tail. We'll put this up next to the start symbol since it's identical. Technically we could just use start here because we're not using epsilon, but let's not get into that. And this is our regular grammar. Here's how it looks as a tree, which is kind of interesting. It's a binary tree with a very specific pattern of having a terminal on the left and a non-terminal on the right. I don't really have anything particularly insightful to say about it. I just thought it was pretty neat that regular expressions, languages, grammars, parsing and trees all connect up in this way. And I bet that's worth knowing for some reason, so let me know if you have any idea what such knowledge will be useful for. It's also worth pointing out that the previous grammar and this grammar both work and they both describe exactly the same language. They do have different pros and cons though. This grammar proves to us by following Chomsky's rules that the language is regular, but the previous grammar probably better represented our intuitive sense of what the structure should be. Okay, so back to regular expressions. One sort of funny but perhaps obvious thing about regular expressions is they are not in themselves a regular language. This means that regular expressions can't recognize valid regular expressions. Basically, if a language needs to have balanced brackets, it's not going to be regular, and the previous video covers this in a little more depth. So we need a more powerful kind of grammar to recognize regular expressions, and the answer to this is to take one step up the Chomsky hierarchy to context-free grammars. For context-free grammars, every rule has to be in this form. This basically means a non-terminal on the left, and on the right you can have any sequence of non-terminal and terminal symbols in whatever order or quantity you like. That vertical bar means or, and the grouping with the asterisk of course means repeat 0 or more times. A significant fraction of your typical programming language can be recognized by a context-free grammar, which means the basis for most parsers is context-free grammars plus some extra bits. You may be thinking, that seems like a pretty permissive rule, I can't possibly imagine what the next level up might look like. Well, permit me to shock and terrify you with the rule for context-sensitive grammars. To prepare you, I'm going to abbreviate non-terminal to non-term and introduce a new symbol sec to mean sequence of terminal and non-terminal symbols. Okay, so this is the same thing before, just slightly shorter names. Now let's take a look at the rule for context-sensitive grammars. What this means is that how non-term will be rewritten will depend on what's before or after it. To recognize context-sensitive grammars, we need something as powerful as a Turing machine, which I guess is why the bits of programming language syntax that fall outside of context-free grammars tend to be custom-coded. Anyway, fortunately the regexes we're going to deal with today are context-free. Let's build up a little grammar for them on the right. We're going to start with our start symbol, which produces either a non-terminal expression or an empty string signified by epsilon. Then we'll define expression to be either a single term or a term followed by an expression. This recursion allows us to express a sequence of terms. Now here we're using a very basic form of Bacchus-Naur form. There's also many other dialects and they're typically referred to as extended Bacchus-Naur form, and they allow for easier syntax to denote things like one or more, like asterisks or whatever, but we're going to keep it very basic for now. Next, we'll define a term as either an item followed by a modifier or an item alone. Item might be a single character like A, or it could be a group surrounded by brackets. It can be modified by, for example, a Kleene star, denoting 0 or more repetitions of the item. Then we'll define modifier to be either an asterisk or a plus symbol, and those are our first terminal symbols. We'll then define item as either a character or a group. Character is fairly straightforward. It's essentially going to be any character that isn't a meta character in regex, so all the letters, digits, and symbols that are not part of the regex syntax. For simplicity though, we're going to forget about symbols. I've written it out for you so you can see what it's doing, but most of the time when you're working with parsers, you'll have some system available that enables you to define these as a range. Finally, we'll define group as an opening parenthesis, followed by an expression, followed by a closing parenthesis. This is the rule that makes it not a regular grammar. Now we can use this grammar to produce a string. I'll just let you watch this speed by. I've got an ad lib in my script here, so I guess I better say something for as long as I think it's going to take to rewrite everything. I hope you're enjoying this. It's all coded out. It's all kinds of fun to write this stuff. And here's how it looks in a tree. A little more complex than the last tree, but still nothing compared to how complex some abstract syntax trees can get. The question is, how do we generate such a tree automatically from a string? And there are many answers to this question with different trade-offs. We're going to use the method people typically reach for first, called recursive descent. We'll look at recursive descent in the abstract first, taking a very simple grammar as our example. The basic idea with recursive descent is that we begin with the start symbol and then try rewriting rules and check if our terminals line up with the target string. If they do line up, we keep going, and if they don't, we backtrack and try a different rule. So let's see it in action. We'll begin with start, and we use the first rewriting rule to expand this to an H and a tail. We then look at the first terminal symbol to check if it matches our string, and it does. So we take the remainder of the string, AA, and move down the tree and to the right to see if the tail can match that. We check again whether the terminal symbol matches our string. It does, so we expand tail with the remainder of the string once again, and once again it picks the first rule in the list. Once more we check whether the new terminal matches, and it does, so we expand tail one more time to see if it can match an empty string. However, this time when we check the terminal symbol, we find that it does not match. We conclude that the last rule expansion must have been a failure, so we roll it back. We try the second rule in the list for expanding tail, but this also isn't any good. Even worse, we have no more rules to try for expanding tail, so we conclude that even the previous rule expansion must have also been a failure, and we roll that back too. We try the alternative rule for expanding tail, and fortunately, this time we have a match. We check that we've reached the end of our string, and we have, so we have a successful parse. You may be thinking that the whole last half of the parsing process was completely unnecessary, and it was patently obvious which rule we should have chosen. And you'd be right. The backtracking behavior of this algorithm is definitely a disadvantage, and it can lead to some really horrible slowdowns. There are a variety of other approaches to parsing which avoid this issue, often involving writing a grammar which a tool then converts into a sophisticated parser for you. Recursive descent's big advantages is that it is simple to implement, easy to understand, and since we can implement it in everyday code rather than using special purpose tooling, it can also be optimized and extended relatively easily. These are some of the reasons that Clang and GCC use handwritten recursive descent parsers. And that's not just because of their age. Rust, Golang, and I think also Zig use variations of recursive descent. JavaScript engines from V8 to Bun use recursive descent parsers as well. They'll glue many additional techniques into the algorithm for performance and functionality and error handling, but this is the core idea. Let's implement it in some code. To implement recursive descent in code, we take each of our non-terminal symbols and turn it into a parsing function and a representation, for example a class or a struct or something like that. We'll start with the character rule. If we're working in Python, we can make our representation a data class, but of course the tool you reach for will vary depending on how you're implementing this. Then we need to create our parsing function, whose job is to take a sequence of symbols and return either none if there's no match, or if there is a match to return the representation and the rest of the symbols still not parsed. We can implement a modifier in the same way. Things get more interesting when we implement a rule with a non-terminal on the right-hand side. Let's take item for example. We'll forget about group at first and just assume that it only produces a character. We can give it a representation fairly easily. When we implement the parsing function, we'll first need to check whether the character parser is actually successful, and then if it is, we can just wrap the result in our item representation along with the remaining symbols. If it isn't, we return none as before. And of course we don't need to call this function twice, we can find a way to do that more efficiently, but it makes the code a little cleaner on the screen. So use your imagination. To add in group, we're first going to need to imagine that we've already written a parser for it, which hopefully we can manage, and then we add it to the type of item.content. We then add a second if block after the first in our parser. We've made two critical decisions here. The first is that we've decided to write a backtracking style parser. That's one that will try a match, and then if it doesn't parse, it will go back and try a different match. These can become unworkably inefficient, as I discussed before, but they're also nice to write, so we're sticking with them. But it's worth you knowing that the typical alternative to backtracking here is called predictive parsing and involves looking ahead to see which is going to be the best choice. The second decision that we've made is that we've given the character match a higher priority than the group match. If the grammar is ambiguous, meaning that it could be valid to match either character or group, then this may have a significant effect on the result. But since our grammar is pretty straightforward, we won't have much trouble. Let's move on and look at group. Its representation is once again fairly straightforward, though we do have to imagine that we've already written the expression parser. There's one difference that's so small you might not even notice it. We don't preserve information about the bracket terminals. This is because we don't actually care and we can rederive them anyway if we need to. The parsing function here has to be just a little smarter than before. First, we check whether the first token is an opening bracket. If it is, we try to parse an expression, and then if that works too, we check whether the next token is a closing bracket. And if all of that works, we have a match and we return our group along with all the symbols after the closing bracket. Otherwise, we return none. If you're seeing this drift to the right, or the edge case handling or the backtracking issues, and you're starting to feel a little bit itchy, I agree with you. Even in this quite simple grammar, we're starting to run into code that feels a little bit iffy. A lot of parser tooling and development is about finding ways to make this kind of code go away, or at least manage it better. And you're welcome to try, but right now we're going to move on. Let's look at term. We'll represent term as having an item plus an optional modifier. And then to parse it, we'll first need to try to parse an item. And then if that succeeds, we'll try to parse a modifier. And then if that succeeds too, we'll return a term with both. If the modifier doesn't succeed, we'll return a term without a modifier. And if none of that succeeds, we return none. Note that this parser is greedy. It tries to match the longest sequence it can. If we instead wrote this to parse an item alone first before parsing an item with a modifier, our parser wouldn't actually work. It would just always jump to the item without a modifier match, and we'd have an asterisk we wouldn't know what to do with. So in this case, the greediness is good for us. Let's look at expression. Expression is unique in this program in that it can expand to itself. It can either expand to a single term or a term and then an expression, which might itself be another term, and then an expression, and so on. If you squint a bit, this starts to look a bit like a list, and if you squint a little more, a linked list. We could decide to add a feature to both the grammar and our parser that would make this explicit, and many grammar systems do. But actually, due to the way we implemented our regex engine, and particularly the concat function in the last video, it's pretty convenient to keep it this way. So we will. We'll pick a representation for expression, something like this seems fine, and then set about writing our parser. We'll check first whether we can match a term. And if we can, we'll try to match an expression. If we're successful there, we'll return an expression with both. Otherwise, we'll return an expression with just the term, and if none of that works, we'll return none. It's all pretty similar to what we did with item. It's also greedy like item was, but there's a gotcha here that I want to point out. This grammar is what's called right recursive. That means that the recursive part, expression in this case, comes after the first symbol. We could implement a left recursive grammar by swapping those terms over, and then swapping them in the code too. See if you can spot the problem. When I was teaching, I would always wait for a little bit here and see if anyone's faces would light up. I don't know, I still like to do it in the videos, even though I know you're probably just staring, waiting for me to get on with the next bit, but do you see it? I hope you see it. I'll get on with it. The first thing this parser does after it gets called is call itself, so it's going to recurse forever. Not good. So the classic thing people say about recursive descent parsing is that it can't handle left recursion. So easy, just don't do left recursion, right? Well, sometimes left recursion is pretty convenient, in particular when it comes to parsing arithmetical expressions. So to use my real catchphrase of this video, we'll probably come back to that in future. But for now, let's put everything back to right recursion since we don't really need left recursion here. This only leaves our start rule to implement, and it's not so difficult. And there it is. Of course, you can simplify it, but I thought it'd be good to keep it to the structure we've seen before. Finally, we'll write a parse function to wrap everything up and do some basic error handling. And that's recursive descent. We now have a syntax tree which can then be transformed into our finite automata from last time. Or you could just get this parser to generate that graph directly if you preferred. I'll put the code plus a few edge cases I ignored here and some nicer error handling on the ODE's website linked in the description. This is probably a decent account of parsing and it's definitely enough to go away and practically build some languages, but I'm not quite satisfied. I have a little rule of thumb in my head about programming that if you implement a lower level idea using a higher level tool, there's a decent chance that you've accidentally introduced some circular logic into your understanding. It could be that you don't really understand the idea at all, that you're just leveraging the ideas embedded in the tool. It's not always the case, but it's typically worth checking if you can actually implement it or at least explain it using a lower level set of ideas. So we could go and write all this in assembly and satisfy ourselves that way. This feels manageable to me, except for one part. We haven't yet introduced anywhere near the necessary data structures to produce a syntax tree. So in a sense, my intuition is right. There's a big bit we're skimming over here, but it's also, once more, something we're going to have to come back to. I needed to decide whether to do a chapter on data structures or languages first, and I decided on languages. So we can't quite build a parser from scratch yet, at least not in assembly. But there's no reason that we can't build a recognizer, something that will tell us whether a regex is valid or not. One of the interesting things about recursive descent is that it leverages the idea of recursion. If you watch the Stacks video, you'll remember that recursion was championed into the world of programming by Dijkstra, and this is one of the many ways that his slightly sneaky tactics were vindicated. And one of the lessons from that video is that whenever you see a problem being solved with recursion, you should think, this problem is really being solved with a stack. You may also remember that the Chomsky hierarchy prescribes a certain machine which can recognize each type of language. For regular languages, that is the finite state automaton, whereas for context-free languages, it is the pushdown automaton. And the pushdown there refers to a stack. So for all of these reasons, in a programming language without recursion, like assembly, we can implement a recognizer using a stack instead. So let's do that. To begin, I'll show you a handmade finite state automaton which can recognize a subset of regular expressions. Just the character C and the Kleene star, which can only come after the character C. The basis of this finite automata is that a regex can be in either a modifiable state or a non-modifiable state. A modifiable state is where we've got a character or a group which can be modified by a Kleene star or a plus or something like that. And a non-modifiable state is when we can't put a plus symbol or an asterisk or anything like that. So for example, if we're at the start of a string, we can't put an asterisk there because we've got nothing to modify, but if we put a character there, we could then put an asterisk after that. Let's see it play out in the automaton. The start symbol goes straight to non-modifiable with an epsilon transition because we can't modify until we've got a character to modify. And in case you need a reminder, an epsilon transition just means we can always follow it and it does not consume a character of the input. Whenever we're in a non-modifiable state and we see a character, we switch to the modifiable state, since it will be possible to then modify that with an asterisk. And when we're in the modifiable state, we can accept further modifiable characters, so we create a loop back to the modifiable state. And whenever we see an asterisk, we switch back to non-modifiable, since we can't modify an asterisk. And we're going to forget about the plus symbol for now because it behaves essentially the same. And both the modifiable and non-modifiable states can go to the final state with an epsilon transition. This finite state automaton can now recognize regexes with characters and asterisks properly. Note that in these visualizations I've cut out a few of the epsilon states that just fail immediately, so feel free to pause this video and try out some strings manually if you like. This automaton can't yet handle grouping, and no finite number of additional states can help us with that. That's essentially what Chomsky's taxonomy is all about. That to describe a certain power of language, you need a certain power of grammar to match, and you need a certain conceptual machine with a matching power to recognize languages within that grammar. But we can build on this to create a pushdown automaton which can recognize regexes with grouping. For this, we need two new things, a stack and a new kind of rule. Here's our new stack, and here's one of our new rules. This rule has a new kind of notation. The symbol before the comma indicates what has to match in the string, just like in all of our other rules. Here it's an epsilon, which means we don't need to match anything. After the comma, we have a funny arrow relationship. We'll call the symbol before the arrow the pop value, and the symbol after the arrow the push value. The pop value is compared to the symbol on the top of the stack. If they're the same, that symbol is popped off the stack. Here it's an epsilon again, which means we don't have to match anything or pop anything. If the rule matches, not only do we change state, we also push the push value onto the stack. So this rule ignores the input string, ignores the stack, and pushes a Z or a Z onto the stack. The Z here is just a symbol to mean end, and it isn't related to the input string at all. We also amend the rule from non-modifiable to final to do the opposite. This rule ignores the input string, checks if Z is on the top of the stack, and if it is, pops it off but doesn't push anything. These two rules alone will match an empty string. You'll see that this Z becomes useful because we only want to reach our final state when the stack is empty. We'll need 4 more rules. The first two handle the situation where we meet an opening bracket in our regex. The start of a bracket is non-modifiable, since you can't open a bracket and put an asterisk straight there without having something to modify. For this reason, we add a rule from modifiable which goes to itself and pushes a B onto the stack. We can also accept a bracket from a modifiable state, and in that case we transition to non-modifiable and also push a B onto the stack. We can also accept a bracket from a modifiable state, and in that case we transition to a non-modifiable and push a B onto the stack. When we see a closed bracket, we pop a B off the stack. After we see a closed bracket, we of course could put an asterisk, so we're in a modifiable state. So we have a rule for the modifiable state going back to itself, and for the non-modifiable state to the modifiable state. And that's it. We've now got a pushdown automaton which can recognize regexes with grouping. Pay attention while you watch this to the way that the stack is used to store the number of brackets we're inside at a time. If we try it out with a faulty regex like this, which has no closing bracket, you'll see that we end up with a B on the stack rather than a Z, and that means non-modifiable can't progress to the final state and the match fails. Feel free to pause the video and try out your own examples. If we tweak it a little by getting the start and final transitions to match on a null terminator rather than the epsilon, we can also make it deterministic. Determinism isn't guaranteed with pushdown automata. It isn't the case with like finite state automata where there's always going to be a deterministic equivalent, but since we can do it in this case, we have a very nice pathway for implementing this in assembly. All we need to be able to do is match on a character, have a stack which we can push to, pop from and peek at the top of, and these are all things we know how to do, or at least know how to do if you watch the assembly video in the last chapter. Here's what my implementation looked like at the end. This is all done using assembly macros, and I think it looks pretty nice. If you don't know what macros are, all they are is a little function which gets called at compile time to expand this code to something else. Here's my rule macro. The macro essentially gets copied to where the call came from, and its arguments get interpolated into that code. You could write all this out longhand, but then it would definitely not fit into the video frame, and I guess that's a concern for me. Hopefully you can see though that this is all fairly straightforward assembly. We load a byte into a register, we compare it against things, we look at things on the stack. We're not doing anything really wild here. With these techniques, we can implement any deterministic pushdown automata in assembly, and therefore a recognizer for any context-free grammar, which I think is pretty cool. So this video, like all those videos, comes with some resources and exercises so that you can try this out yourself. The exercise for this video involves parsing and evaluating a special language. This language involves digits and brackets, but not the normal brackets you might be used to. These are brackets based on letters, so a capital A opens a bracket and a lowercase a closes that bracket. The brackets are all unique, so there are essentially 26 different kinds of brackets. So an expression like this evaluates to this. Now for this exercise, we want to evaluate each string in the language into a number. So we have an evaluation strategy, which is fairly simple. Things next to each other get added together. But the brackets have some extra behavior. You take the number in the alphabet that letter is, so A1, B2, C3, etc., and you add it to all of the digits inside its brackets. So if we evaluate the final A in this sequence, we get 3 plus 1. With nested brackets, we need to make sure that we reflect the letter values with each digit within. So with the 6 here, we need to reflect that it's inside a B, so 6 plus 2, and also that it's inside a C, so 6 plus 2 plus 3, and then C5 as you'd expect. All of this comes out to the final value, 23. Your task is to make a parser and evaluator for this language and to use it to evaluate some strings on the OATS website. You can find the link to that, which will contain this exercise in written form, as well as some resources and a special extra exercise for members linked in the OATS description. I also want to thank all the OATS members out there for supporting me to make these videos, and I hope you enjoy the extra exercise which builds on this in kind of an interesting way. Next time we're going to be finishing up this little segment on regexes, I think that's still where we are, and having possibly a bit more fun with automata and seeing what else we can do with them. See you next time, and thanks for watching. Laters.